Now let's discuss delta zigzag star connection, which is the very important topic from winding connections. Zigzag connection is used where delta connection is weak. It is known that the main drawback in delta connection is there is no neutral connection in it, so it can't be used for three-phase 4-wire system. Whereas coming to zigzag connection, it can provide the same phase displacements as that of delta connection, and moreover it provides neutral connection, so it can be used for three-phase 4-wire system, and also it can handle large unbalanced loads. Whatever the phase displacements that we got with delta connection, we can obtain the same from zigzag connection. That is, zigzag connection can provide the same phase displacements as that of the delta connection, and moreover it has neutral connection, so it can be used for three-phase 4-wire system, which is not possible with delta connection. So is why zigzag connection is preferred where the delta connection is weak. And generally zigzag connection is used on LV side of transformer, and as zigzag connection is having neutral connection, it is used for grounding transformer. And zigzag connection has no triplet harmonics problem. It is known that whether it is star or delta connection, in phases there will be triplet harmonics, and to eliminate those triplet harmonics we need to provide the path. In star connection, that path is provided by connecting the neutral connection to the ground, whereas in case of delta connection, the closed loop itself will act as a path for the triplet harmonics. So in star connection and delta connection, by providing the paths to the triplet harmonics, we are avoiding the triplet harmonics. And coming to zigzag connection, there are no triplet harmonics problem, because in this connection the windings are connected in such a way that the triplet harmonics becomes 0. Now let's see how the triplet harmonics in zigzag connection are reduced to 0. In zigzag connection, each phase winding is divided into 2 windings. Let us consider ABC phase sequence. So this is the A phase winding, which is divided into 2 halves, and similarly B phase winding is divided into 2 windings, and C phase winding is divided into 2 windings. So from this you can observe that zigzag star connection winding is divided into 2 halves. These 3 are considered as one half of the zigzag star connection, and these 3 are considered as the other half of the zigzag star connection. Now let's give the notations to these windings, and let us consider these as dot and terminals of the windings, and the dot and terminals are given the notations small a2, small b2 and small c2, and to this half portion small a4, small b4 and small c4, and the non-dotted terminals are small a1, small b1 and small c1. And coming to this side of half portion, small a3, small b3 and small c3. Here the notations are given in smaller case because we consider the zigzag star connection in LV side. To avoid confusion, let's assume that primary is HV and secondary is LV. Okay, so here on LV side we are having zigzag star connection, so is why the notations we took in smaller case. In zigzag star connection, one of the half of LV winding is connected in star, so is why zigzag star connection is also called as interconnected star connection. And here that star connection can be obtained either by joining the non-dotted terminals to a common point and giving it to ground, or by joining the dotted terminals and connecting it to ground. Here for star connection, let's consider the dotted terminals as common end terminals and connect these 3 to the ground and give it the notation N. As zigzag star connection is having star connection internally, So is why it is also called as interconnected star connection. And why it is zigzag means in each phase of zigzag star connection, it consists of two different phases and which are connected in phase opposition. And why the two windings in each phase of zigzag star connection are connected in phase opposition means to reduce the triplet harmonics to 0. So to obtain zigzag connection, let's connect this half portion of LV winding with this half portion of LV winding such that the two different phases must be connected in phase opposition. So observe that this is the non-dot end terminal. So to have the phase opposition connection with other winding, we need to connect this non-dot end terminal of this phase to the non-dot end terminal of other phase. So let's connect the non-dot end terminal A1 with the non-dot end terminal B3. To have phase opposition connection, we need to connect two non-dot end terminals or we need to connect two dot end terminals. Okay, here we are connecting the two non-dot end terminals. Okay, now let's connect the non-dot end terminal B1 with non-dot end terminal C3 and now non-dot end terminal C1 with non-dot end terminal A3. Okay, so here the three phases in zigzag star connection are A4 to N and B4 to N and C2 to N. So these are the three phases in zigzag star connection, and if you observe that in each phase of zigzag star connection there are two different phases. That is, if you consider A4 to N, the two different phases are A phase winding and C phase winding, and these two windings are connected in phase opposition. That is, we join the non-dot end terminal of A coil with non-dot end terminal of C coil. And why these two windings are connected in phase opposition means to reduce the triplet harmonics to 0. Therefore, the phase voltages in zigzag star connection are VA4N, VB4N and VC4N, in which each phase voltage is the vector sum of two different phases offset by 120 degrees and connected in phase opposition. So if you consider VA4N, okay, which is the vector sum of this voltage and this voltage, these two are of different phases. This is A phase and this is C phase, and these two windings are offset by 120 degrees and these two windings are connected in phase opposition. Now let's see how the triplet harmonics in zigzag star connection are reduced to 0. Let us consider this is A phase and this is B phase, which are connected in phase opposition. So to have phase opposition connection, we need to connect two dot ends of the coils together or two non-dot end terminals of two coils. Okay, here we connected two dot end terminals of the two coils. So is why these two coils are said to be in phase opposition. We are considering this as A phase and we are considering this as B phase. And for just a moment, let's consider the C phase also. When the EMFs are induced in these three coils, the EMF induced in A phase will have the fundamental induced EMF plus the triplet harmonic. Similarly, the EMF induced in B coil will have fundamental EMF plus the triplet harmonic, and similarly in C coil the induced EMF will have fundamental induced EMF and the triplet harmonic. And it is known that in three-phase ABC phase sequence, the fundamental induced EMFs will be at an angle 0 degrees and EB will be at an angle minus 120 degrees from EA, and EC will be at an angle minus 240 degrees from EA, which means if EA starts at 0 instant, then after 120 degrees EB will start, and for further after 120 degrees EC will start. And now coming to these triplet harmonics, E3A will be at an angle 0 degrees and E3B will be at an angle 0 degrees and E3C will be at an angle 0 degrees. These triplet harmonics are also called as zero phase sequence harmonics because they have a phase displacement of 0 degrees with each other. Therefore, these triplet harmonics will start at same instant. Now let's take off the EC coil and consider only A coil and B coil. If suppose EA is equal to EB and E3A is equal to E3B, as these two coils are connected phase opposition and these are having equal voltages, therefore the voltages gets cancelled and the resultant voltage will be 0. But the logic here is that the voltages which are getting cancelled are the E3A and E3B, that is triplet harmonic voltage, because at that instant these two are present, E3 and E3B, because they start at same instant. But coming to the fundamental induced EMFs, at that instant only EA is present, therefore the resultant voltage will be EA, and after 120 degrees there will be EB, means now the resultant voltage will be EB. Therefore, if we connect the two different phases coils in phase opposition, only here triplet harmonics are reduced to 0. Therefore, from this we can say that with this type of zigzag connection, the triplet harmonics will get reduced to 0. Therefore, because of these reasons, zigzag connection is used where the delta connection is weak. Now let's get into our discussion on delta zigzag star connection. So let's have the HV windings in horizontal fashion. Let these be the dot ends and let's give the notations. And as this delta connection is on HV side, therefore the notations are in capital letters, and dot end notations are given capital A2, capital B2 and capital C2, and non-dot end terminals capital A1, capital B1 and capital C1. And here we are considering the delta connection by joining the non-dot end terminal with dot end terminal, non-dot end terminal with dot end terminal, and non-dot end terminal with dot end terminal, and taking the connections from dot ends. So this is the delta zigzag star connection. Now let's draw the phasor diagrams for delta zigzag star connection. So coming to delta connection, if you consider this as VA phase, and the terminals for this primary side VA phasor are A1 and A2, and on primary side as the connection is took from dot end terminal, that is A2, therefore arrow will point towards A2 and the other end will be A1. In three-phase ABC system, if VA is taken as a reference, then VA will be at an angle 0 degrees and VB will be at an angle minus 120 degrees from VA, and VC will be at an angle minus 240 degrees from VA. So as we consider this VA phasor like this, therefore in clockwise direction at an angle minus 120 degrees, there will be VB phasor. Let's consider the VB phasor somewhere here like this, and now let's decide the terminals of this VB phasor, and observing winding connection that B1 and B2 are the terminals of this B phase, and as the connection is took from dot end terminal, that is B2, therefore arrow will point towards B2 and other end will be B1. And in primary side winding connection, A1 is connected to B2, means in the phasor diagram to A1 there must be B2 end. Therefore place this phasor such that A1 will have B2 end. So this is the VB phasor, so other end will be B1. Now let's draw the VC phasor. So VC phasor will be at an angle minus 240 degrees from VA, or we can take VC at an angle minus 120 degrees from VB. So as this is considered as VB phase, so from this in clockwise direction at an angle minus 120 degrees there will be VC. So let's consider this as VC phasor, and now let's decide the terminals of this VC phasor, and observe in winding connection that C2 is the connection we took from, therefore arrow will point towards C2 and other end will be C1, and observe in winding connection that to B1 there is C2 connection, so here there must be C2. So place this phasor here such that B1 will have C2 connection, so this is the C1 end. And now in delta connection, for comparison or reference purpose, we need to consider the imaginary neutral connection. It is known that there will be no neutral connection in delta, but for comparison or reference purpose we need to consider imaginary neutral, and here that reference phase to neutral voltage is A to N, because connection is took from A to. So this is the phasor diagram for this delta connection. Now let's draw the phasor diagram for this zigzag star connection, and to avoid confusion, let's indicate the voltages in each winding. So let this be VA X1, let this be VB Y1, let this be VC Z1, and this voltage be VA X2, this be VB Y2, and this be VC Z2. Observe in zigzag star connection that this half of LV winding is star connected. So first let's draw the phasor diagram for this star connection, and it is known that the secondary side phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA X1 phasor parallel to primary side VA phasor, and now we need to decide the direction of the secondary side VA X1 phasor, and the direction of phasors depends on the connections we took on primary side and secondary side. And observe that on primary side the connection is took from dotted terminal, and coming to the secondary side in this coil, connection is took from non-dotted terminal, means the secondary side phasor direction is opposite to primary side phasor. So VA X1 phasor direction will be like this. Now we need to decide the terminals of this secondary side VA X1 phasor. So as the terminals are A1 and A2, and the connection is took from non-dotted, that is A1. Therefore arrow will point towards the connection we took from. So here A1, therefore arrow will point towards A1, other end will be A2. And now let's draw the VB Y1 phasor. So drawing secondary side VB Y1 phasor parallel to primary side VB phasor somewhere here, and now we need to decide the direction of secondary side VB Y1 phasor. And observe that on primary side connection is took from dotted, and on secondary side here the connection is took from non-dotted, means the direction of secondary side VB Y1 phasor is opposite to the primary side VB phasor. Therefore the direction is like this. Now we need to decide these phasor terminals, so B1 and B2, and of this, as the connection is took from non-dotted, that is B1, therefore arrow will point towards B1 and the other will be B2. Now observe in binding connection that to A2 there is B2, means to A2 terminal there must be B2. So place this VB phasor such that A2 will have B2. Therefore like this. This is VB Y1 phasor, and this end is in B1. Now let's draw the secondary side VC Z1 phasor. So drawing secondary side VC Z1 phasor parallel to primary side VC phasor like this. And now we need to decide the direction of secondary side VC Z1 phasor. And observe that in this primary side the connection is took from dotted, and in this secondary side the connection is took from non-dotted, means secondary side VC Z1 phasor direction is opposite to primary side VC phasor. So direction is like this. Now we need to decide the terminals for this VC Z1 phasor. So as the terminals are C1 and C2 and connection is took from non-dotted, that is C1, therefore arrow in this phasor is pointing towards C1. So other end will be C2. And now observe winding connection that to A2 and B2 there is C2 connection, means here there is C2 connection. So draw this VC phasor such that A2 and B2 will have C2. So like this. And the common notation for A2, B2 and C2 is given small n. So this is the phasor diagram for this internal star connection. Now let's draw the phasor diagram for this half portion of LV winding. And observe that to A1 there is B3 connection, means to A1 there must be B3. Therefore we need to draw the secondary side VB Y2 phasor parallel to primary side VB phasor. So drawing the secondary side VB Y2 phasor parallel to primary side VB phasor somewhere here like this. And now we need to decide the direction of secondary side VB Y2 phasor. And observe that on primary side the connection is took from dotted, and on secondary side the connection is took from dotted, means the direction of VB Y2 phasor is same to that of primary side VB phasor. So like this. And now we need to decide the terminals of VB Y2 phasor. So the terminals of VB by 2 phasor are B3 and B4, and as the characteristic from dot end terminal, that is B4. Therefore, arrow will point towards B4 and other end will be B3. So now, in this phasor diagram, draw this VB by 2 phasor such that A1 will have B3. So, like this. VB by 2. And now, the resultant voltage is VB4N. Now coming to this B1 connection, B1 is having C3, means to B1 there must be C3 connection. Therefore now we must draw the VCZ2 phasor. So drawing the secondary side VCZ2 phasor parallel to primary side VC phasor somewhere here like this. And now we need to decide the direction of this VCZ2 phasor. So observe that in primary side characteristic from dot end, and on secondary side characteristic from dot end. Therefore, the secondary side phasor direction will be same to that of primary side phasor. So the direction is like this. And now we need to decide the terminals of VCZ2 phasor, and the terminals are C3 and C4. And as the arrow points towards the connection we took from, therefore arrow will point towards C4. Therefore other end is C3. Now draw this VCZ2 phasor such that B1 will have C3. So like this. This is C4 and this is the VCZ2 phasor. Therefore here the resultant voltage is VC4N. And now coming to C1 connection, C1 is having A3. Therefore C1 must have A3. Therefore now we need to draw VAX2 phasor. So let's draw the secondary side VAX2 phasor parallel to primary side VA phasor somewhere here like this. This is VAX2. And now we need to decide the direction of VAX2 phasor. So observe that on primary side characteristic from dot end, and on secondary side characteristic from dot end. Therefore secondary side phasor direction is same to that of primary side phasor. So like this. Now we need to decide the terminals of VAX2 phasor. So here the terminals are A3 and A4, and the characteristic from dot end, that is A4. Therefore arrow will point towards the connection we took from, that is A4. Other end will be A3. Now draw this VAX2 phasor such that this C1 will have A3. So like this. This is A4. Therefore now the resultant voltage is VA4N. Therefore this is the phasor diagram for this type of delta zigzag star connection. And from this phasor diagram, the phase voltages of zigzag star connection are VA4N, VB4N and VC4N, which are the resultant voltages of two different phases and which are offset by 1 degrees and which are connected in phase opposition. Now let's identify the vector group symbol for this delta zigzag star connection. And it is known that the first character in vector group symbol is in capital letter, and that will indicate the HV winding connection. Here it is delta, so capital D. And now the second character in vector group symbol is in smaller case, and that will indicate the LV winding connection. And here the LV winding connection is zigzag star connection. So to represent that, it is taken in small z. And the third position of vector group symbol is a numerical, which will indicate the LV winding phase neutral voltage displacement with respect to HV winding phase neutral voltage. So on LV side, the phase neutral voltage, let that be A4N. Okay, here we are comparing the A phase. So here on LV side, the phase neutral voltage is A4N, and on HV side, the phase neutral voltage is capital A2N. If you consider this as the clock, let this be the numericals on the clock. In vector groups, the HV side phase to neutral voltage is always taken as reference, and that is indicated with minutes needle in clock. And as the HV winding phase to neutral voltage is taken as reference, therefore minutes needle is always shown pointing towards 12. And in vector groups, the LV winding phase neutral voltage is represented with hours needle in clock. And to know the LV side phase node voltage displacement with respect to HV side phase node voltage, we need to superimpose this diagram on this and observe the phase node voltage of HV side and LV side. So if you observe that HV side phase node voltage is like this and LV side phase node voltage is small a4n. It is taken as short because LV side phase node voltage is represented with hours in clock. And now to know the phase displacement, place this diagram in clock such that HV side phase node voltage is along the minutes needle in clock. So upon placing this diagram in this, hours needle will be shown pointing towards clock, and this position represents 0 clock hours. So therefore, the numerical in this vector group symbol is 0, which will indicate the LV side phase node voltage displacement with respect to HV side phase node voltage, and that is obtained by the angle between minutes needle and hours needle in clock. So here the angle between minutes needle and hours needle is 0. Therefore, for this type of connection, we got a phase displacement of 0 degrees. Delta zigzag star connection has 6 possible connections. Means we can have delta zigzag star connection in 6 ways. One of the way is this, and with this we obtain a phase displacement of 0 degrees. And in this video, we are not going to see all the 6 possible connections. Okay, here we are going to see only the 2 main possible connections. So this is the one of that main possible connection from which we got the 0 degrees phase displacement. Now let's see the second possible connection of delta zigzag star connection. In that the change is only in star connection. In this connection, we join the dot end terminals and took the connections from non-dot ends. And now in second possible connection, what we are doing means we will join the non-dot end terminals and we will take the connections from dot end terminals. Let's see that. Let's consider these LV windings like this. Let this be the dot ends. These 3 are the half portion of LV winding and these 3 are the remaining half portion of LV winding. And the notations given are small a2, small b2 and small c2. This is small a4, small b4 and small c4. And the non-dot end terminals are given as small a1, small b1, small c1. And this is small a3, small b3 and small c3. And to avoid confusion, we are considering the voltages in each winding. So this is VA x1, this is VB y1, this is VC z1, and this is VA x2, VB y2 and VC z2. For this HV winding delta connection, this is the phasor diagram. The only change that we are making in second possible connection is in star connection. In first possible connection, we joined the dot end terminals and took the connections from non-dot end terminals. And now we are joining the non-dot end terminals together and grounding it like this, and we are taking the connections from dot end terminals. And now we must join this A phase winding with the B phase winding of this half section, and these 2 windings must be connected in phase opposition. So here this is dot end. So to have the phase opposition, we must connect this dot end to the dot end of this phase. So let's join the dot end A2 with dot end B4 and dot end B2 with dot end C4, and similarly dot end C2 with dot end A4. This is the second possible connection of delta zigzag star connection. And now we need to draw the phase diagram for this delta zigzag star connection. And coming to this HV winding, we didn't change any connection, so the phase diagram is left as it is. Now let's draw the phase diagram for this zigzag star connection. And of this, first we must draw the phase diagram for the internal star connection. First let's draw the secondary side VA x1 phasor parallel to primary side VA phasor like this. This is VA x1 phasor. And now we need to decide the direction of secondary side VA x1 phasor, and the direction depends on the connection we took on primary side and secondary side. So here the connections took from dot end, and here on LV side the connections took from dot end. Therefore the direction of secondary side VA x1 phasor is same to that of primary side VA phasor. Therefore like this. Now we need to decide the terminals of VA-X1 phasor. So as the terminals are A1 and A2 and the connection is took from dot end, that is A2, therefore in phasor diagram arrow will point towards the connection we took from, that is A2, and the other end will be A1. Now we need to draw the secondary side VB-Y1 phasor. So let's draw the secondary side VB-Y1 phasor parallel to primary side VB phasor somewhere here like this. And now we need to decide the direction of this VB-Y1 phasor. And coming to the primary side, the connection is took from dot end, and on secondary side the connection is took from dot end. Therefore the direction of VB-Y1 phasor is same to that of primary side VB phasor. And now we need to decide the terminals of secondary side VB-Y1 phasor. So the terminals are B1 and B2 and the connection is took from dot end, that is B2. Therefore arrow will point towards B2 and other end will be B1. And observing binding connection that to A1 there is B1 connection. So in phasor to A1 there must be B1. Therefore draw this VB-Y1 phasor such that A1 will have B1. Therefore the VB-Y1 phasor is like this. And now we need to draw the secondary side VC-Z1 phasor. So let's draw the secondary side VC-Z1 phasor parallel to primary side VC phasor somewhere here like this. And now we need to decide the direction of secondary side VC-Z1 phasor. On primary side consists took from dot and on secondary side consists took from dot. Therefore the direction of secondary side VC-Z1 phasor is same to that of primary side VC phasor. And now we need to decide the terminals of VC-Z1 phasor. Here the terminals are C1 and C2 and the connection is took from dot and terminal, that is C2. Therefore arrow will point towards the connection we took from, that is C2, and other end will be C1. And now observing binding connection that to A1 and B1 there is C1 connection, means in phasor diagram to A1 and B1 there must be C1. Therefore draw this phasor diagram such that A1 and B1 will have C1. So like this. This is C2. This is C1. This is VC-Z1 phasor. So this is the phasor diagram for internal star connection, and the common notation given here is small n because it is on LV side. Now let's draw the phasor diagram for this half portion of LV winding. So observe that to A2 there is B4 connection, means in phasor diagram to A2 there must be B4, means we must draw the phasor diagram for VB-Y2 phasor. So let's draw the secondary side VB-Y2 phasor parallel to VB phasor somewhere here like this. And now we need to decide the direction of secondary side VB-Y2 phasor. And observe that on primary side consists from dot end and on secondary side consists from non-dot end. Therefore the secondary side phasor direction will be opposite to primary side phasor. So as primary side phasor is towards this direction, so secondary side phasor direction will be like this. This is VB-Y2 phasor. And now we need to decide the terminals of this VB-Y2 phasor. So the terminals are B3 and B4 and they consist from non-dot end, means the arrow will point towards the connection we took from, that is B3. Therefore this is B3 and other end will be B4. So draw this VB-Y2 phasor such that A2 will have B4. So like this. This is B3 and this is VB-Y2 phasor. And now the resultant is VB3N. Now to dot end B2 connection there is C4 connection, means here to B2 there must be C4, means we need to draw the VC-Z2 phasor. So let's draw the secondary side VC-Z2 phasor parallel to primary side VC phasor somewhere here like this. And now we need to decide the direction of VC-Z2 phasor. So observe that on primary side constituted from dot end and on secondary side constituted from non-dot end, means the direction of secondary side phasor is opposite to primary side phasor. So this is the direction of VC-Z2. And now we need to decide the terminals of VC-Z2 phasor. So the terminals are C3 and C4 and the connection is took from non-dot end, means the arrow will point towards the connection we took from, that is C3, and other end will be C4. Now draw this VC-Z2 phasor such that B2 will have C4 connection, means the phasor diagram is like this. This is C3. Therefore the resultant voltage is VC3N. And now in this winding connection to dot end C2 there is A4 connection, means to C2 there must be A4. That is, we need to draw the VA-X2 phasor. So let's draw the secondary side VA-X2 phasor parallel to primary side VA phasor, somewhere here like this. And now we need to decide the direction of VA-X2 phasor. And observe that here on primary side consists from dot end, and on secondary side consists from non-dot end, means the secondary side phasor direction is opposite to primary side phasor. So the direction of VA-X2 is like this. And now we need to decide the terminals of this VA-X2 phasor. So the terminals are A3 and A4, and they consist from non-dot end, that is A3. Therefore arrow points towards the connection we took from, that is A3, and other end will be A4. Therefore draw this VA-X2 phasor such that C2 will have A4 like this. This is A3. Therefore the resultant voltage is VA3N. This is the phasor diagram for this type of delta zigzag star connection. Now let's identify the vector group symbol for this type of delta zigzag star connection. And it is known that the first character in vector group symbol is in capital letter, and that will indicate the HV side connection. Therefore first character is in capital D, and the second character in vector group symbol is in smaller case, and that will indicate the LV winding connection. Here it is zigzag star, so to represent that it is taken in small z. And now we need to decide the third position of vector group symbol, which is a numerical, and that numerical will indicate the LV side phase to neutral voltage displacement with respect to HV side phase to neutral voltage. And here on LV side the phase to neutral voltage is VA3N, because the three phases of zigzag star connection are VA3N, VB3N and VC3N, and here we are comparing the A phase. Therefore the LV side phase to neutral voltage is VA3N, and HV side phase to neutral voltage is A to N. In vector groups, the HV side phase to neutral voltage is taken as reference, and that is indicated with minutes, needle and clock. Therefore as the HV side phase to neutral voltage is taken as reference and is represented with minutes, needle, therefore it is always shown pointing towards 12. And LV side phase to neutral voltage in vector group is indicated with hours needle in clock. Okay, and to know the numerical in vector group symbol, let's superimpose the LV side phasor diagram and HV side phasor diagram and observe the phase to neutral voltage of HV side and LV side. So if you observe that HV side phase to neutral voltage will look like this, and LV side phase to neutral voltage will look like this. It is taken as short because the LV side phase to neutral voltage is represented with hours needle in clock. Therefore if you place this diagram in this clock such that this HV winding phase to neutral voltage points towards 12, then the hours needle will be shown pointing towards 6, and this corresponding position will represent 6 o'clock. Therefore the numerical in vector group symbol is 6. So this is the vector group symbol for this type of delta zigzag star connection, and here this 6 will indicate the LV side phase to neutral voltage displacement with respect to HV side phase to neutral voltage, and that is given by the angle between minutes needle and hours needle. So if you measure in anti-clockwise direction from minutes needle, it will be 180 degrees, or if you measure in clockwise direction from minutes needle, it will be minus 100 degrees. Therefore with this type of delta zigzag star connection we got a phase displacement of 180 degrees, and with previous case we got a phase displacement of 0 degrees. Now let's know the phase voltage ratio and line voltage ratio of delta zigzag star connection. Let small v1 be the primary side phase voltage and small v2 be the secondary side phase voltage. That implies the transformation ratio constant K is equal to small v2 by small v1, which means v2 is equal to K into small v1. And as in zigzag star connection, each phase winding is divided into two equal windings, means in each winding the voltage can be taken as K V1 by 2. That is, here this voltage is K V1 by 2 and the voltage in this winding is K V1 by 2. From this phase diagram we can see that the phase voltages for the zigzag stack connection are VA3N, VB3N and VC3N. So let's consider VA3N, which is the vector sum of the voltage induced between C1 and C2 and A4 and A3, and the voltage between C1 and C2 is VCZ1, and the voltage between A4 and A3 is VAX2. And for simplification, let us assume that all the windings voltages are same, therefore that can be taken as equal to K into V1 by 2 plus K into V1 by 2. And now if you apply the triangle law of factors, then that can be taken as equal to root over K into V1 by 2 whole square plus K into V1 by 2 whole square plus 2 K into V1 by 2 K into V1 by 2 into cos theta. And from this diagram, the theta angle is 60 degrees. Therefore, solve this, that cos 60 degrees is 1 by 2. So, that implies 3 into K into V1 by 2 whole square square root. That will give you root 3 times K into V1 by 2. Therefore, the relation we got is V A3N is equal to root 3 times K into small v1 by 2. And now by rearranging this equation, V A3N by small v1 is equal to root 3 times K by 2. V A3N is secondary side phase voltage and V1 is primary side phase voltage. Means here the phase voltage ratio of delta zigzag stack connection is root 3 by 2 into K. This is the phase voltage ratio of delta zigzag stack connection. And now coming to line voltage ratio of delta zigzag connection, let capital V2 be secondary side line voltage and capital V1 be primary side line voltage. And on secondary side, this represents star connection. Therefore, the relation between the line voltage and phase voltage for star connection is secondary side line voltage V2 is equal to root 3 times the secondary side phase voltage. And here the secondary side phase voltage is VA3N. So, which is equal to root 3 into K into V1 by 2. Therefore, place this here, root 3 into K into small v1 by 2, which will give you 3 into K into small v1 by 2. And now observe the primary side connection, that it is a delta connected. Therefore, the relation between line voltage and phase voltage for delta connection is line voltage is equal to phase voltage. Therefore, primary side line voltage V1 is equal to primary side phase voltage, that is small v1. Therefore, replace small v1 with capital V1 here, that is equal to K into capital V1 by 2. And now rearrange this, capital V2 by capital V1 is equal to 3 by 2 into K. Therefore, the line voltage ratio of delta zigzag stack connection is 3 by 2 into K. And if you consider K is equal to 1, and observe that the secondary side line voltage V2 is equal to 1.5 times the primary side line voltage, which will tell you that the secondary side line voltage is 50% more than the primary side line voltage. Means delta zigzag stack connection is used for step up applications. Therefore, this is about delta zigzag stack connection.